Okay, good morning, everyone. Today is the lecture 7 of our class. So before the lecture, I want to give some brief summary about a question I was asked about the homework and also about the confusion for hierarchical ANOVA. Actually, both are related to hierarchical ANOVA. So, and the function ANOVA in R. So specific to, let me try to say that hierarchical. Okay, so what we know is that if you want to get hierarchical ANOVA table, ANOVA from just running a linear model in R, you could do something like this. So if you write y tilde x1 plus x2 plus x3, so then what this function will return to you, you can try this yourself, is that it will be a hierarchical ANOVA table. So the first row will correspond to the sum of squares with x1 as the only predictor. And then we will have the sum of square with 2 given 1. And also sum of square of 3 given 1 and 2. So you will have that hierarchical sequence. Then the question is, what does each of them stand for? So for example here, that this is the source of variation, right? And then we will have the SSR, so those kind of things. So sum of square regression. So then the first question is, what is this SSR1? So then I would need to have the degrees of freedom and then the MSR. That's the SSR divided by the degree of freedom. And finally, I will have the F-statistic. So the first question, which is the confusion, is how do we compute SSR? So if we think of the model, actually in this hierarchical ANOVA, we will have 3 models. The model 1 is to have x1 as the only predictor. So let's just write the fitted coefficient as y hat equals, let me put it, beta 0 hat 1. 1 means model 1 plus beta 1 hat 1 x1. That's our fitted model 1. And our fitted model 2, let's write it as y hat equals beta 0 hat 2, stands for the intercept for fitted model 2, plus beta 1 hat 2 x1 plus beta 2 hat 2 x2. Okay, and then we'll have model 3. I write as y hat equals to beta 0 hat 3 plus beta 1 hat 3 x1 plus beta 2 hat 3 x2 plus beta 3 hat 3 x3. So we will have the fitted coefficients for each of the 3 models. And then when we actually compute this SSR1, we only use the fitted model 1. We're not using anything related to fitted model 2 or fitted model 3. So SSR1, using x1 as the only predictor, is the variance in the response that can be best explained by the fitted model 1. Okay, so that here, it will be equal to summation. Let me use the scalar form, I from 1 to n. So SSR is the explained part, right? So that will actually be this one. So that's the explained regression part. So I would have yi is our observed response minus the fitted response, which is minus beta 0 hat 1 minus beta 1 hat 1 x1 squared. That will be my SSR. So please know that you're not going to use beta 1 hat 2 or beta 1 hat 3. So you're not going to use model 2 or model 3. even though you are doing this hierarchical ANOVA. So let me just write it here. It's not equal to 2 or it's not equal to the third one. Yi minus beta 0 hat 3 minus beta 1 hat 3 x1. X1, sorry, I forgot I here. I should put X1 I here and X1 I here. Yeah, so that would be the SSR1. And then SSR2, SSR1, 2, okay? So given only 2 predictors in the model, it will be based on the theta model 2. Yi minus beta 0 hat 2 minus beta 1 hat 2 x1 1i minus beta 2 hat 2 x2i squared. That will be the SSR1, 2. So then finally, SSR1, 2, 3 is I from 1 to n, yi minus beta 0 hat 3 minus beta 1 hat 3 x1i, oops, sorry. Yeah, that's right. Beta 2 hat 3 x2i minus beta 3 hat 3x3i squared. So in other words, whenever we have the model, we are going to use the fitted coefficients for the model that includes the predictors we are interested in. So therefore, SSR1 is just this. And then for the 2 given one, it will be defined as SSR1, 2 minus SSR1. And for the last one, it will be SSR1, 2, 3 minus SSR1, 2. So you are going to take difference between 2 nested models, adjacently nested models. The degrees of freedom for each one, we know that this is the number of parameters. So I would say this degree of freedom is 1, right? Because in model 1, we have one additional parameter in addition to the intercept. You always need to subtract an intercept. And for 2 given 1, we have an additional degree of freedom. For 3 given 1, 2, we have an additional degree of freedom. So therefore, here the MSR is just this one divided by 1 for each. So in terms of the nominal value, it's equal to the SSR. So finally, the F-statistic, okay? So the F-statistic is something trickier. So we know that this is equal to, so maybe let me put it here, MSR1, okay? So this is, okay, so this is MSR 2 given 1, MSR 3 given 1, 2. So for F-statistic, we know it's defined as, this is the basically MSR1, okay, over MSE. So that's the trickier part. So here, when we are doing this hierarchical ANOVA, what R does is to divide this by the SSE of 1, 2, 3, the full model, divided by the n minus the number parameter in the full model. So that's n minus 3. This is what R does. Okay, and then this one is MSR 2 given 1, divided by SSE 1, 2, 3, n minus 3. Finally, MSR 3 given 1, 2, divided by SSE 1, 2, 3 over n minus 3. So previously, what I said is that we only look at this row. That makes more sense. So this row means that given 1 and 2, what's the additional contribution of predictor 3? So I said that this is equivalent to doing a t-test for the coefficient of predictor 3, whether S3 has a 0 coefficient or not. And this is also equivalent to when we do a wall test or likelihood ratio test by comparing So what test is also can be done for just coefficient of x3 being 0 or not. Even though it's more general, it can be applied to a subvector of beta. And likelihood ratio test can be used to compare model 2 and model 3 because model 2 is nested under model 3. Even though these tests may give you slightly different p-values, but they are conceptually the same, testing the same null hypothesis. Now, the question is, how about this one, the first F-statistic, and the next one? So I said that we don't want to use it because it's a little confusing. The reason why I said it's confusing is that if you consider, okay, versus if I do just ANOVA of LM with y tilde x1 plus x2 only. If I do this, okay, then I can tell you that for the first row, if I still call that SS1, so SSR1, this stays the same. DF is also 1. MSR stays as is. And finally, the F statistic will be different. If you only include 2 predictors in this R function, it will be equal to MSR1 over SSE12. The model includes 2 predictors over M minus 2. So you see that these two F statistics, if you compare this versus this, you will see that they are different things. So the difference lies in the denominator. So this one, I call this 1, it's going to estimate that sigma square variance error variance by using the residual sum of squares from the full model divided by the degree of freedom in the full model. Well, here we're going to use the model for 1 and 2 only. So model 2, we're going to use it to derive the estimation for sigma square. So that's what the post I shared with you, which was shared with me by Kangcheng in our class, is about. So it's basically saying that these two can be considered as 2 statistics, okay? So let's just call it 2 statistics. One is about, I'm writing here, MSR1 over SSE123 over n minus 3. The other one is, I call it F2, MSR1 divided by SSE12 over n minus 2. So if you look at the formula, they are not the same. And if you calculate these 2 statistics on one particular data set, you can try this yourself. They are also mostly different, right? They're only equal to each other in special cases. So in this case, why do we have both? And what one do we use in practice? So my take for this is that, so if you read the post, you can see that there's a very interesting thing to learn. That is, if you truly believe that your model only has x1 with non-zero coefficient, in other words, in the model, let me write it. So if you write yi equals beta 0 plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus epsilon I. Okay, so this is the model. So if you believe under the null hypothesis that beta 2 and beta 3 are both equal to 0. In other words, you believe that in your true model, there's only one predictor x1. So in this case, both the F1 and F2 can be used as test statistics. It's just that they have different degrees of freedom. So I can say that F1 would follow, let me see if I'm right. Yeah, so both F1 under the H0, so you follow a F distribution with degree of freedom 1 and n minus 3. This is the distribution for F1 under the null hypothesis. And for F2, you follow the null distribution with degree of freedom is still 1, but n minus 2. So in other words, you're going to compare, so each of those two statistics will follow its own null distribution. But what will be different is that these two test statistics will not be equal to each other in nominal value. In other words, if you think of this question as, so from the frequentist perspective, so a valid test statistic means what? It means that given its null distribution, when the null is actually true, you will only have 5% of the chance that the corresponding p-value you compute for the test statistic will be less or equal than alpha, the significance level you set. So each of them may have 5% of chance across repeated sampling. But on one particular data set, each of them will receive one realization. And this realization can be different. So that means on average, they both have 5% of rejection if the null is true. But in reality, it's not the same. So the realization will be different. So that's what that post was trying to explain. But what I want to say is that if you are really interested in comparing model 1 versus model 2, so if you're interested in comparing these two things, the common statistic we use is trying to basically compare, or maybe I give a very good example. So if you are interested in comparing model 1 and model 2, okay, probably I changed it, my bad. I think this confuses you further. Let me see where I can fix it. Okay, probably, yeah, maybe you can ignore this part for now. Ignore this part for now. So let me just restate the question. I think that would be more straightforward, sorry. So what I'm saying is that if you're interested in the null hypothesis in this true model, okay, the true model is this one. If you're interested in whether beta 2 is equal to 0, right? In terms of that, you're trying to compare whether in model 1 versus model 2. So in other words, you want to see whether you only need x1 or you need both x1 and x2. This is what I want to say. So then the common practice is still to do the ANOVA of LM y tilde x1 plus x2. This is the common practice. In other words, you try to compare model 1 versus model 2. And it's not a common practice for you to look at the second row in this hierarchical ANOVA with three predictors. So if you want to, I will write it down. So looking at ANOVA with LM y tilde x1 plus x2 plus x3. So even though the second row over here can also have a valid explanation as what I just said, but this is not a common practice. This is the common practice. That's the take-home message I want to offer here. So that's why I do not recommend using that hierarchical ANOVA table for your model comparison. Instead, I think it's better that you use this notation. So in R, you can do ANOVA, let's say LM y tilde x1, LM y tilde x1 plus x2. So you directly put the two models you want to compare against each other into the ANOVA function instead of running the hierarchical ANOVA to get a result. This would be what I recommend that you do. Okay, but the reason I want to say this here in today's class is because I want to emphasize that frequentist interpretation, that is, two test statistics may be both valid, but they could have different realizations on one particular data set. Therefore, they may lead to different decisions, whether you reject the null or not on one particular data set. So we need to realize that in the frequentist statistic, a rejection we made on the data set is random because the data set itself is random. Even though this is a little counterintuitive, but that's the nature of frequentist statistics. In other words, when we say that, okay, significance level alpha, we are talking about this testing procedure when it's applied to infinite data sets and averaging the result. So overall, over all the repeated samples, we will have 5% or alpha chance that we reject the null hypothesis by mistake. But we cannot really say, okay, this particular rejection on one data set is reject or not. We can never say that with frequentist statistics. Okay, hopefully this makes sense. Do you have any questions about this part?
I have another question about the homework.
Yeah.
I was wondering, so when the homework asks to like conduct a wald test or t-test, do you want us to report the p-value, or do you want us to set an alpha and then reject or not reject?
So if you set alpha to say 5%, then you will be able to say, okay, given this alpha and given the p-value of this test, I will reject it or not. But if you do not want to preset the alpha, you can just report the p-value. So what I would say is that I would just say, okay, given this p-value of this t-test, this p-value of the wald test, what my decision would be for, say, this alpha and another alpha. So I'm just going to give alpha as an example. You know, the reason why I would say this is something I discussed with other people yesterday. It's very interesting about why we need a p-value. So if you think about it, if you have the significance alpha, you can directly find the rejection region of your test statistic, right? You can say whenever my observed test statistic falls into this region, I will reject the hypothesis, null hypothesis. So it seems that p-value is not really necessary. That's not a necessary concept for statistical tests. But then if you think about it again, you will see, okay, the reason why p-value concept was invented is because it's for convenience. That means we do not need to preset an alpha. We can just calculate p-values by converting the observed test statistic value into a p-value. Then the user can set alpha based on what they need, right? So they can set alpha to be 0.1, 0.05, 0.001, up to their need, and then they can cut the p-value. So I think it's invented for convenience. But one thing that actually really confused people is this. Maybe I can just add this as a side note. So for everyone's thought, especially I think for PhD students who is interested in statistics or PhD student in statistics, this is very important to think about. So do you think these two concepts are the same? So the probability of reject the null hypothesis given the null hypothesis is true. This is one probability. And the other thing is p-value. Do you think these two things are equal or not to each other? Yes, I think I saw people nodding, nodding the head. So Li Feng, I saw that you are nodding your head. Maybe you want to say why you think it's correct. Why do you think that these two are equal?
Is it the same? Not
Yeah.
sure.
Not sure. Okay. Yeah, probably I didn't make it very clear. So here the thing is that we need to evaluate a probability, and it's a probability conditional on the null being true. And it's about an event. That event is rejection. So here it depends on how do we make the rejection. Okay, so what we mean by significance level is that the significance level alpha is preset. And we want to set alpha to the probability that we reject H0. Okay, this is an event given that the conditional probability that the null is true. So then given this, we can go from alpha to the rejection region. Okay, so we can get a rejection region of test statistic. So we find the rejection region so that its conditional probability is exactly equal to alpha. But on the other hand, what's p-value? P-value has nothing to do with alpha. You don't need an alpha to compute the p-value. Versus the p-value is the probability that if you reject the null hypothesis at the observed t, let me call this test statistic with capital T for the random test statistic value. And if we reject H0 at t or more extreme values of t, under the null hypothesis, that will be the p-value. So in other words, the key thing here is what means more extreme, right? This one, the definition of extremeness will depend on the alternative hypothesis. For example, when you are doing a two-sided t-test, then having a value that is more extreme than t in both tails, that is being very negative or very positive, are considered more extreme. So that will be your rejection region. And then you're going to evaluate that probability. Or if the alternative is one-sided, greater than, you're only going to have very positive values as more extreme. So it depends on how you define the more extreme based on alternative hypothesis. But basically, this p-value is just it's just based on two things. One is the distribution of the, so it depends on two things. One is the distribution of t, right? Distribution of t under the null hypothesis. That's one thing. And the second thing is the observed value of the test statistic on your data. It only depends on those two things. And it's not depending on alpha. It does not require the alpha. So p-value was proposed for convenience. You can consider it as a conversion. It converts the observed value t to a value between 0 and 1. So later, you only need to compare p-value against alpha to make a decision. You no longer need to use the original observed statistic t or the null distribution. So these information are all incorporated or combined into this p-value. On the other hand, if you do not have the concept p-value, you just have alpha, then the rejection region will be based on a range of values for the t. So whenever you have a data set, you compute t, and then you compare the observed value with the rejection region. If it falls into the region, you reject, otherwise you do not reject. And these two approaches are equivalent to each other. So one take-home message I want everyone to know is that these two things are not the same, because one is given that you define the rejection region already. You evaluate this probability. That's what you call the significance level. The other is what you have p-values based on one particular data set. And this one, this alpha, maybe I'll write it here. This alpha, this one, does not depend on a data set, okay? So when you talk about significance level, you are talking about this procedure in general. It has nothing to do with one particular data set or one particular decision. So hopefully this makes more sense now. So what do you think, Livon? Are you convinced?
Yeah, understand. Thank you.
Yeah, thank you. Yeah, I think this is very important for those of us who teach the introductory statistics courses. I think it's so confusing for people who first learn statistics. Okay, so let's get back to our theme, the logistic regression. The logistic regression is what we opened up last lecture. Let me find the notes. So this is what we have. So what we said is that here, the response is binary. We first talk about logistic regression for binary data. The response is binary, 0 and 1. And again, we consider two layers in our structure. One is random structure, That is, how is the random variable yi distributed around its mean? Here we mean the mean, we use the pi I to denote the mean. And then we said, okay, let me enlarge this. And then we said that for the mean, we need to assume a systematic structure. So it's about the relationship between the mean and the linear and the predictors. Okay, so we assume that there's some transformation of the mean that is linear with the predictors. So we call this part linear predictor, xi transpose beta. And this transformation on the mean, we call it a link function. It is monotone and invertible. So specific to logistic regression, this is the link function. For the mean, for Bernoulli, it's a probability between 0 and 1 for the probability of getting 1. So the link function is called a logic function. It's basically log pi I over 1 minus pi I. We assume this is a linear function of the predictors x1 to xp minus 1. And this logic function takes this form. When pi I is getting close to 1, it goes up to infinity. When pi I is going down to 0, it goes down to negative infinity. So doing this transformation, we can make this systematic structures, both sides have to have the range as the real line, from negative infinity to positive infinity. So their range just matches. Otherwise, if we don't do transformation, pi I is constrained to 0 to 1, while xi transpose beta can go from negative infinity to positive infinity. So their ranges do not match. Okay, that's the logistic regression for binary data. And we know that it is a very popular method for classification. So we're going to talk about the parameter estimation, which is here the parameter of interest is beta. We're going to talk about that later. But now let's talk about another form of logistic regression, which is also very useful in practice. So I'll call this the logistic regression for group data. So what do we mean by group data? So you can consider the group data as aggregation of binary data by predictor values. So if two binary responses have, or I would say, maybe not two, I'll call it Ni. If Ni binary responses have the same predictor values, Xi transpose, then group them. So this can be more easily seen in the social science context. Let's say that I have Ni respondents to a survey, and they have the same age, gender, education level, if these three are my predictor values. And if I have Ni people, they share the same predictor values. So same age, same gender, same education level. Then I group them into one group, because if you look at their rows, corresponding rows in the design matrix, these people will share the same rows. And then in other words, it's not really meaningful or necessary or effective to keep those identical rows, right? Because basically they mean the same thing in my matrix and they do not contribute to the row rank. So therefore I just combine them into one row, and then I will add up these people's binary responses, and I will call that as yi. So therefore, I will have yi follows a binomial distribution. And the binomial distribution is with a total of Ni people, and the success probability is still pi I. So I group them. So therefore, the yi is no longer binary, but it's a count that varies between 0 and Ni. Okay, that will be my new observation. And then the I will be the ith unique predictors, or I can call that the ith group. Okay, so in other words, you can think of the groups as just the reduction of the design matrix by removing repetitive rows in the design matrix. So then my n here would be equal to the number of groups. Okay, this is the new random structure for group data. And for systematic data, systematic structure, sorry. This is random structure. This is systematic structure. It's still the same thing. Logit pi I over 1 minus pi I. This is equal to xi transpose beta. Okay, so it's the same thing, but we can use the logistic regression for group data. And if you check the GLM function in R, you can actually see that it allows you to input group data, not just binary data. There's an option for specifying that, and that's very useful. And another example for the group data, if you think about it, is that, so let me just make it up. So for example, in genetic study, and if you say that I have people whose predictors are the same, and here the predictors can be like your genetic materials, your genotype. In other words, if they have the genotype the same, but you check their phenotype, like whether they have a disease or not, you can group people by the genotype. So let's say for people with one genotype, let's say out of 100 people with that genotype, 50 of them carry the disease, versus for another group of people with another genotype, and out of say 50 people, 49 of them have the disease. So if you compare these two groups, you want to say, okay, does this genotype difference really associate with the phenotype, with the occurrence of disease? This is another question that can be addressed by this group data logistic regression. So you see in the first group, the percentage of people having the disease is 50 over 100, right? 50%. While the second group is 49 over 50, that's 98%. So you can see the difference is very big, but whether this big difference is statistically significant or not, you can answer this question by running logistic regression and check whether that genotype predictor has the coefficient 0 or not. Okay, so that's it. And then how do we interpret how much this pi changes as my predictor value changes? To evaluate this question, we need to restore the relationship between pi I and xi transpose beta. So we know that this is one way to write this systematic structure. Another way is to write pi I as exponential xi transpose beta divided by 1 plus exponential xi transpose beta. Okay, and we know that in this xi transpose beta, it's this. It's basically we have the summation, okay, j from 1 to p. It's xij times beta j. Okay, here I'm just considering xi1 to be 1. This is for the intercept, okay? Intercept. So the first columns are all 1. So starting from the second one is a real predictor value. So if I want to evaluate how much does the jth predictor contribute to changes in pi I can do this. So that is partial derivative of pi I against xij. So this is about if I change my xij a little bit, how much will the corresponding pi I changes? And we can see that based on this formula, we do the partial derivative, we will be able to see this is equal to beta j times pi I times 1 minus pi I. This is for logistic regression. And what does this mean? It means that the effect is not just depending on the coefficient beta j, but also depending on the current value of pi I. If pi I is 0 or 1, then the jth predictor will have no effect at all. And the effect of jth predictor will be maximized when pi I is equal to 0.5. When it's 1/2, the effect is the maximum. So the key thing is to know that effect depends on the current value pi I. On the other hand, if we think about linear model, in the linear model, the systematic structure is mu I equals xi transpose beta, right? The mean of yi is directly a linear function of predictors. So in this case, if I do partial mu I against partial xij, the effect of jth predictor is just beta j. It's a constant, and it's just a coefficient, and it does not depend on mu I, on the current value of mu I. You see, this is a very big difference between these two things. And you can see why this makes sense. Here, the pi I is constrained on 0 or 1, right? Constrained between 0 and 1. So therefore, you see, no matter how much the value you change in the predictor, once it reaches down to 0 or reaches up to 1, it cannot change anymore. Otherwise, it's no longer constrained between 0 and 1. However, if you think about the mean in linear model, the mu I can go from negative infinity to positive infinity. So it can vary freely. So therefore, there's no such constraint on it at all. Okay, so this is very important for our interpretation of the effect of a predictor on pi I. So we should not just say the effect is equal to beta j, because beta j itself is not constrained. Okay, now we have introduced two forms of logistic regression, for binary data and for group data. Now let's talk about the key thing, parameter estimation. Estimation of beta, this beta coefficient vector. Again, we're going to use the maximum likelihood approach. So let's first write down the likelihood. And similar to what we have for linear model, here the likelihood is only based on the random distribution, the distribution of the random variables y1 to yn. And they are actually assuming to be independent across I. So here the likelihood for the beta, right? And we know the parameter here is pi, which has a relationship with beta. So let's first write down the likelihood of pi first, and then we will replace pi by beta. So first, consider pi as the parameter. So the likelihood is defined as the joint density y1 to yn given the pi parameter. And because of the independence, we can write it as the product of each yi's marginal density given pi. And this marginal density or probability mass function, more precisely, because yi is 0 or 1, just two values, will be based on the Bernoulli distribution. Let's just use the Bernoulli for binary data first. That's simpler. Okay, so I'm going to say that this is for yi binary. I'm not writing the form for group data. So for Bernoulli, that probability mass is equal to pi I to the power yi times 1 minus pi I to the power 1 minus yi. We know this general form because when yi equals 1, we get probability pi I. When yi equals 0, we get probability 1 minus pi I, and only one of them will appear. Okay, so we can actually obtain the log likelihood by taking the log. That can simplify the form by moving down the exponent. So L pi can be written as summation, product becomes summation, and pi yi goes down. We get yi times log pi I and plus 1 minus pi 1 minus yi. 1 minus yi times log 1 minus pi I. That would be the log likelihood. Okay, and we can simplify this a little bit by combining the two terms both involving yi. So I'll combine the log pi I with the minus, so log pi I with the minus log 1 minus pi I. So this will give me yi times log pi I divided by log pi I, because log minus is equal to division within log plus log 1 minus pi I. This is the log likelihood function. And now I'm going to use the relationship between pi I and beta. So I can rewrite this likelihood function for log likelihood for beta. So this is just to replace pi with beta. And one thing I want to emphasize here is that for this formula to go from pi to beta, we just need to replace each pi I by this function of beta. We don't need to add any change of variable formula as we did for the probability density function transformation. If you recall, that's the thing we use when we introduce the Box-Cox transformation. We talk about the change of variable formula for density functions when we replace one variable by another. Here, we don't need that Jacobian to be multiplied. The reason is that the log likelihood function is not a density function of pi. This is not the density of pi. This is not the density of beta. So we don't need that change of variable. We're just talking about replacing one expression by another. So this can help you see, okay, this likelihood function is just a function. It's not a probability density function. So therefore, let's use that relationship. And we know based on the systematic structure, this is just equal to xi transpose beta. Beta appears. And for this one, I'm going to use this conversion, this equivalent expression. So 1 minus pi I is equal to 1 over 1 plus exponential this. So in other words, I can easily see this is equal to minus log 1 plus exponential xi transpose beta. Okay, so now I write down the log likelihood as this. So then what's left is to find a maximizer for this function. And that maximizer is what we are going to call it as beta hat. And please note that here this beta is a p-dimensional vector. So we're going to find the p coordinates as the maximizer. Okay, that's here. So then if you see that it becomes ultimately just an optimization problem. How do we maximize this p-dimensional function? And so this has been a very big problem, in the pre-computer age. In the pre-computer age, everything needs to be calculated by hand. Then we need to, the way we approach this problem is to check whether this function is concave. If it's concave, we're trying to derive it through a gradient, right? The gradient is a p-dimensional vector, and we set it to 0 to solve for each one. If it doesn't have a closed form, which is the case for here, if it doesn't have a closed form, which means that we cannot easily set the gradient to 0 and solve for the p coordinates in beta hat, then we need some computer algorithm to do that, to solve this optimization iteratively. And that's the general case for GLM model, generalized linear models as GLMs. Logistic regression is just the first case. And we know that in the linear model, even though we can also address the MLE problem as an optimization problem, but that's easy. We have a closed form solution. So we can write beta hat as x transpose, x inverse, x transpose y, right? We can do that. But here we do not have a closed form. So we need an optimization algorithm. Okay, so that's the thing I want to introduce for logistic regression. And we're going to introduce the general optimization algorithm for GLMs with exponential family as the random structure next. So which means that we're going to move on to the GLM theory as our next topic. But for now, do we have questions about the logistic regression part we have covered? So 2 parts, one for binary data, the other for group data. Okay, so if no more questions, let's move on to the GLM theory, for which logistic regression is just one special case. So to start with the generalized linear model, let's revisit the linear model as a start. We always use linear model as the most intuitive thing and the motivation for GLM. So in the linear model, if we think about its random structure, it's normal distribution. So yi's are independently follow normal distribution with mean mu I and a common variance sigma squared. And the systematic structure is that mu I is equal to xi transpose beta. That's the linear model. Now we want to move on to GLM, generalized linear model. So we're going to need changes for both. One is the random structure, the other is the systematic structure. So for the random structure, we are going to assume that each yi are independently following an exponential family distribution, again with mean mu I, and the common auxiliary parameter, which is not of our interest, but probably needed for distribution specification. We call that phi. That's what we change for the random structure. So it's a generalization of the normal distribution. And you can see that this phi is not always needed. For example, in logistic regression, Bernoulli or binomial, both only need one parameter related to mu I, and we call that pi I, the success probability. And we don't need another parameter. And we can also see that later we'll talk about Poisson regression. For Poisson distribution, we also only need one parameter as the mean. So Bernoulli and Poisson are one parameter exponential families. But we also have 2 parameter exponential families like normal. You need the mean and you also need the variance. You can consider variance to be this additional parameter. And for example, gamma distribution, it needs 2 parameters. And negative binomial distribution, it also needs 2 parameters. So we're talking about exponential family with 1 or 2 parameters in general. And we do not cover the more complicated case where you need more than 2 parameters. And for the systematic structure, we need a change. That is, it's not just mu I directly associated to be equal to the linear function, or we call linear predictor. Instead, we do a transformation G of mu I. Assume this transform mu I is xi transpose beta. So the 2 changes are in the distribution and in the transformation. So the G function, which we call the link function. So we're going to introduce each of them. And in now the modern, or I would say the current GLM theory, this G is uniquely defined given the exponential family. So that means you do not need to worry about how to specify G arbitrarily. And it's actually implied by the density function in the exponential family. So we're going to see that very soon. Okay, so just bear in mind the 2 changes or 2 generalizations we're going to make. So first of all, let's introduce what is an exponential family. I know this is not a very intuitive concept when you first learn it, and I believe that you also encounter it in other core courses if you have taken in our department. So exponential family can be considered as a mathematical abstraction and summary of the common distributions we have learned. So you can consider this to be a summary or unification of common distributions. And by common distributions, I mean normal distribution, gamma distribution for continuous variables, and Poisson distribution for count variables and Bernoulli binary distribution, binomial distribution for Bernoulli for binary and binomial for counts as well. So these can all be considered, and beta distribution for variables continuous between 0 and 1. These are all special cases of the exponential family. And you can see that each distribution's density function can be written as a special form of the density function we're going to write here. So for exponential family, if we just write them as 2 parameters, so 2 parameter exponential family, I'll write the density of yi that follows this distribution with 2 parameters. I'm going to use the notation theta I and phi here. So the form by the name is an exponential function. An exponential function inside the exponent term, we have a ratio. The first one is yi times theta I minus a function b of theta I divided by a function ai of phi, and then plus a function c of yi and phi. So in this density function, we need these, so this is the density of yi given theta I. We need 3 functions inside. So one is the function ai. It's that how we transform the phi parameter. The second is the function b over here. The third is a function c. So function c has 2 arguments. One is yi, one is phi. So these are all known functions. So what we mean is that as long as you can write a probability density function into this form, we can say that distribution is in the exponential family. So that's why it's a mathematical summary of distributions, of a family of distributions. And then how do we interpret those 2 parameters? Theta I can be considered as the location parameter. So a location parameter can be the most popular special case of location parameter is the mean, right? And we can also consider the mode, the median to be other cases of the location parameter. So if you vary the theta I, you're basically shifting your density at different locations. And this phi can be considered as the scale parameter. And the scale parameter has special cases as the variance, or for some distribution, you can consider it's the distance between like the first quartile to the median, the third quartile to the median. If that distribution does not have does not really have the mean or the variance defined. For example, the Cauchy distribution, it doesn't have any moments. You cannot define the mean, but still you can always define a location and a scale. So I would say that, so these 2 parameters specify the distribution. So location is where the distribution is located at, and the scale is how much the dispersion the distribution has. So the key thing to see here is that this density can be separated into 2 terms that multiply with each other, because we know an addition in the exponent is equal to the multiplication of 2 terms, right? And the second term, the key is that it does not involve theta I. So theta I is only in the first term. Another thing is that in the first term, we write it as an exponential of a ratio. And in the ratio, theta I is only in the numerator. And in the numerator, theta I has 2 parts. One is the multiplication with yi. So yi times theta I. This is very important for exponential family. This is the only place where theta I interacts with yi. And the second part is just theta I by itself. So when we are under one family, when we're under one parameter exponential family, we can ignore the denominator. So because phi is not needed, we only have that yi interacting, multiplying theta I, a term as a function of theta I alone, and another term which is about yi alone. So for one parameter, it has a simpler form, yi times theta I minus b theta I plus cyi. And for the two family, we have the phi here and phi here. But phi is not interacting with yi. Okay, so think about the normal distribution or the Gaussian distribution in the linear model. We can see normal distribution is a special case of the exponential family. So if we think about yi, it follows normal distribution with mu I and sigma squared. That's the random structure in linear model. Then we can write fyi. We know its form is root 2 pi sigma exponential 2 sigma square yi minus mu I square. That's the normal density. And if we want to write this in this form, we can see that by some transformation, we can write it as just exponential. And the first term, it gave me yi mu I minus 1/2 mu I squared over sigma squared. So I created this term minus yi squared 2 sigma squared minus 1/2 log 2 pi sigma squared. So by doing this, then you can see that after writing the special form, using general notations for parameters in the exponential family, I would have theta I, in this case, is just mu I, the mean, which is just what we said. This is the location parameter, right? You see the match. And then for the dispersion, we see that it's just here, right? This is the phi. We can just say that phi is sigma squared. And for the b function, b is the transformation of the location parameter. So b theta I is just 1/2 theta I squared, mu I is theta I. And for the a function, ai phi is just phi. It's just the identity function. And the last part is just what we called the c function. And we are not so interested in that, so we don't need to specify that. This is just the c yi phi. Okay, that's just it. So you see that's the exponential family. And in your homework, next homework, you're going to verify that some other distributions are exponential family. So after we summarizing those common distributions into what we call exponential family, we can simplify a lot of calculation because we can derive some general properties about exponential family, and those properties will apply to all distributions in the exponential family. So the most important generalization is what we can say about the mean and the variance of yi if it follows the exponential family. Okay, so these two are the general properties. Properties of this, let me just say, exponential family, theta I phi, the two parameters we specify. So what we said is that if we have a random variable yi that follows exponential family with parameters theta I and phi, then we can immediately say that the expectation of yi is just the derivative of b function at theta I, a very simple form. And the variance of yi is just the second derivative of b evaluated at theta I times this function, the ai function, evaluated at phi. So how do we show this? If we can prove these two, then we can use these properties immediately, and this can make our discussion for the general GLM, the generalized the GLM theory much easier, because later we're going to need expectation and variance for the random variable in the random structure. We're going to need this for that. Okay, so how do we prove it? So the proof is actually based on exchangeability between integration and differentiation. So that's the key. The idea is to exchange integration with differentiation. And we know from calculus that this can only occur when the function is smooth enough. And that's the case for family, for the function whose density, for the function as the density functions in exponential family. So for functions of this form, if we think of it as a function of theta I, okay, think of this as a function of theta I, then it's very smooth. So that satisfies the requirement for this exchangeability. So first thing is to know that given the density function, we know that the integration of fyi given theta I and phi dyi, this is a density function of yi. We know this integral is equal to 1. That's just a fact for probability density function. So now we know that if we take derivative against theta I, so if we take the derivative of this integral against theta I, then of course we are going to get 0 because it's equal to 1, right? Derivative of 1 against anything is 0. So now we need the exchangeability to move the theta I inside the integration. This is the key part. When the f is smooth enough for theta I, we can move this. And in statistics, we call this a regularity condition for the density function. That means this f is smooth enough, so exchange the integration with the differentiation. d theta I, fyi, theta I, phi. Still we have dyi, and this is equal to 0. Then what is this? Then now we need to look at the density form. And using the density form, we need to take differentiation against theta I. And you can see this is the special case for exponential function. When we take its differentiation, we get a copy of this to be retained. And then we just need to get a differentiation of the term inside exponential. And for this term, we know, okay, so when we do that, what's left? We are going to get this term getting differentiated because this term has nothing to do with theta, okay? So then we can see that we would obtain, so this left-hand side is equal to just this term being differentiated against theta I. So we will have yi stay minus beta prime theta I, because this is a function of theta I, and the denominator stays, is not involving theta I. That's it. And then the same exponential term will stay, right? Times the fyi theta I phi, okay, and dyi. That's what we have. And then this term can be separated into two terms, right? So we know this is equal to 0 from here. And now then I know that this term can go away because it's a multiplier and we have 0 here. This can go away. And I can separate this term into two parts. So basically this can give me that integration of yi times fyi theta I phi dyi. That's the first part. It's equal to the second part, and because of negative sign, I move it to the right-hand side. It's equal to And this beta prime theta I has nothing to do with yi. So I can move it out of the integration. The integration is about yi. So beta prime theta I integral fyi theta I phi dyi. Okay, and what's this? The left-hand side is the definition of expectation. So this is expectation of yi. And the right-hand side, this term stays and this integral is equal to 1 by the definition of density. So I have it. So you see, the key thing in this proof is to exchange differentiation with integration. And another key result we use is that the probability density function integrates to 1. And we have this nice result simply because that exponential family density has this nice form as exponential function. Okay, and for the variance, we can prove it similarly. So we just need to take the second derivative against theta I. So for the variance, we need the d squared d theta I squared of the integral fyi theta I phi dyi. This is also 0, right? We just take differentiation again. And once we do that, then we're going to exchange this just like here. So we're going to move this inside. So based on the exchange property, we're going to move the second derivative inside the integration. So d squared d theta I squared of this f function density theta I phi dyi. This will be equal to 0. So we're going to take the differentiation first before we do the integration. And I'm not going to do that again. But basically, you can show that the variance will be equal to this. So it's depending on the second derivative of the b function, as well as this ai function, which is about the transformation of the parameter phi in the denominator in the exponential term. Okay, so then skipping the steps, which is in the notes, you can check it out. In the notes, you can see that basically we will have the variance of yi as the second derivative b at theta I times ai phi. Okay, so we're going to use this result later, but this is good to know for now. Okay, so another thing about this, about the systematic structure. Okay, so coming back here. So let's look at this function for the exponential family here. So in the GLM, we have a convenience here. So that is, we just set the linear predictor. So if you recall, we introduced this notation before. We said that we give this a name or notation, we call this eta I. And eta I is what we call the linear predictor. And eta I is what we have as the linear function of the predictors. So for the systematic structure, we call that canonical link function, which is uniquely determined by the exponential family. So the canonical link function is to set eta I to be equal to theta I in this function. So in other words, this we know in the normal case, okay? In the normal distribution case, theta I is equal to mu I. So the mean is equal to theta I, equal to the location parameter, and we don't need to worry about it. But it's not the case for other distributions that are also in the exponential family. So often the theta I is not equal to mu I, but is equal to some function of mu I. So in that case, we can just directly set, if we set eta I to theta I, then based on the relationship between theta I and mu I, we have that transformation already. So let me try to give you an example. Probably we'll do that next time. So here you can try, I'll leave this as a homework. You can try to write this fyi yi theta I phi for yi follows Bernoulli pi I or Bernoulli mu I, whichever way you prefer. So because the mean is the pi here. So you can try to write it down and see what's the theta I. Then what is the theta I? And you will see that surprisingly, this will be something we use as the link function for logistic regression. So try this yourself after this class. And another question I left for you, but we didn't answer it yet, is in the logistic regression, do we really have an error term? And also this question can also be asked for the generalized GLM. So in the GLM model, the way we specify it, is there an error term somewhere? Okay, so let's come back to this on Thursday. So please bear in mind those two questions before we come back. So that's all for today.